Good morning, students. Welcome back to science class on the chapter work and energy. Okay, so in the previous class we had discussed some problems related to kinetic energy and potential energy. Okay, in this class we discuss law of conservation of energy. Okay, yes, say in the standard we already had studied what is law of conservation of energy. Okay, see this law of conservation of energy, it says that energy can neither be created nor destroyed, but we can convert one form to another form. For example, take electric energy. Okay, so we can generate or we can create electric energy only using hydroelectric energy, thermal power, or wind power, ocean thermal energy. Okay, so here we are just converting one form of energy into other forms. Okay, so that's why it says that energy can neither be created nor be destroyed, but we can transform one form to another form. Okay, see here, for example, I will now take this duster. I will raise this duster to a certain height. Okay. So now at this position, it possesses potential energy. When I drop this one, what will happen? It starts to falling down. Correct? It starts to fall down. Okay. So here, this potential energy is slowly converting into energy. Okay, so here we can say that here we can convert one form of energy into another form. If you take electric energy, okay, and you take one bulb, when you turn that on, when you turn that button on, that bulb, it will blink. Okay, so here that bulb which converts electric energy into light energy and heat energy. When you touch that, if you use that bulb for 1 hour, when you touch that bulb you can feel it, right? So that's why that bulb converts electric energy into light energy and heat energy. Okay, then if you take a fan, okay, so that fan converts electric energy into mechanical energy. Okay, in a hydroelectric, what is that hydroelectric? The flowing water. Okay, so the flowing water, there we will keep turbines. Okay, we will keep turbines, that the turbine it will rotate. Okay, then it generates electricity. Here we are converting hydro energy into electrical energy. Okay, then if you take the thermal power, okay, so thermal means what? Heat. Thermal power plant, there we will burn the coal. There we will burn the coal. Okay, there we will burn the coal. There we are converting heat energy into electrical energy. Then other, take wind energy. We have seen this kind of a fan, the big fan. Okay, correct. So here it rotates, right? By rotating we can generate electricity. Here we can say that wind energy or kinetic and mechanical energy is converting into electrical energy. Okay, so that's why we can convert one form of energy into other forms. So here we can't create energy and we can't destroy, but we can transform one form to another form. In Kanmai, see, just imagine there is one room. Okay, no one is there. If you turn out, if your parents in a wire, they will ask, why are you wasting the bulb? Please turn it off. Okay. See, actually, normally we will say that yes, sir, the current is wasting, but actually according to science the current is not wasting, because here just we are here just that energies, that electric energy is converting into light energy and electric energy. Okay, and see one more here, while converting, we will convert, for example, hydro energy to electric energy. Okay, here converting the before conversion and after conversion. Before conversion and after conversion, the energy remains same. So before converting that energy, for example, before converting energy, say it is 100 joule. Just imagine it is very small. Sorry, 1000 joule. So after conversion, after conversion, the energy may be in another form, but the amount that energy remains same. Okay, it remains 1000 energy only. Okay, so law of conservation, it says that energy can neither be created nor be destroyed, but we can transform one form to another form. And before conversion and after conversion, energy remains same. Okay, so now listen here, we will discuss one simple problem. So this is a ground. Okay, this is ground. So just lift one object. You are lifting here. Okay, so this is height. So now this object here at this position, it possesses potential energy. Okay, that is potential energy is equals to m into g into h. Okay, so potential energy is equals to m into g into h. Okay, so now without any external force, if you drop it, just drop that. See, raise up to here, just drop it. Okay, what will happen? It starts to fall down. Okay, but here slowly, while falling, it is in motion, right? Then it possesses kinetic energy. Okay, then it possesses kinetic energy. Okay, so now here, while falling here, it possesses kinetic energy, that is g equal to half mv square. Okay, so now see here this while falling, this object, it possesses kinetic energy. Why? Because at this position it possesses potential energy. At this position, this object, at this position, this object it possesses potential energy. Okay, so now here slowly this potential energy is converting into kinetic energy. Clear? This potential energy is converting into kinetic energy. Okay, so now here while falling downwards, slowly potential energy decreases and kinetic energy slowly increases. Before reaching the ground at maximum speed, okay, its kinetic energy is highest and its potential energy is least. Okay, just before reaching the ground at the maximum velocity, its kinetic energy is very high and its potential energy is very less, or it is least. Okay, so here when you reach to a certain height, it possesses potential energy. Okay, when it starts to falling downwards, at that time this potential energy is converting into kinetic energy. Okay, at last, see here also while falling downwards, the some amount of potential energy decreases, right? See that same amount kinetic energy increases. Say just imagine here it will start to fall downwards. At that time, say 100 joule, its energy is 100 joule potential energy reduces. Then 100 joule of the same amount of energy, that is 100 joule. That is 100 joule. With 100 joule of kinetic energy increases. Okay. Next, so finally, at last, the kinetic energy maximum and potential energy is least. See here, so here also converting at each and every point, the energy remains same. Just here, this potential energy is converting into kinetic energy. Okay, so each and every point, if you take the energy of the object, that remains same. So this is the law of conservation of energy. Okay, so together the potential energy plus kinetic energy, potential energy plus kinetic energy is equal to constant at each and every point. See, from here, this is your starting point and this ending point. Each and every point, in the absence of external force. So here we have to ignore that air resistance. In each and every point, if you add kinetic and potential energy and kinetic energy, you will get the same answer. If you calculate at this position, if you calculate potential energy plus kinetic energy, you will get the same answer. If you calculate here, you will get the same answer. Here also same answer. Here also same answer. Okay. So that's why, what is that? So potential energy plus kinetic energy is constant in each and every point. That energy remains same. Okay. So before conversion and after conversion, energy remains same. So this is law of conservation of energy. Okay. So what it says, law of conservation of energy can neither be created nor destroyed, but we can convert one form of energy into other forms. Okay, and before conversion and after conversion, energy remains same. So this is known as law of conservation of energy. Okay. Yes. Next, to move to rate of doing work. Rate of doing work. Rate of doing work. Rate of doing work. You know the rate of change of velocity you have heard, right? What is the meaning of rate of change of velocity? The change in velocity in a given time. Rate of change of here, rate of doing work means in a given time how much you will do that work. Okay, see here we'll discuss in the example. Just imagine this is a room. Okay, here 100 chairs are there. 100 chairs are there. Okay, there are two persons, person A and person B. Okay, so now person A will see here the work is both the persons. Okay, both the persons they have to keep 100 chairs outside the room. Outside the room. Now person A to keep 100 chairs outside, he will take say 30 minutes. He will take 30 minutes. Person A takes 30 minutes. And what about person B? Person B takes say 25 minutes. 25 minutes. In 30 minutes, person A will keep 100 chairs outside the room, and person B will keep 100 chairs outside the room. Okay. Now I will ask, who is the strongest, person A or person B? Yes, sir. Definitely we will say that person B is strongest because the person B is also he is also doing the same work in less time, but person A is taking more time. Okay, so but the person B is taking less time, so that's why we can say that person B has more power. Okay, so power means the rate of doing work. Okay, so what is power? The rate of doing work. Okay, so to calculate power, we have a formula. So power is equals to work done divided by time. Work done divided by time. Okay, so rate of doing work is called power. You know, for example, say KTM bike, okay, and City 100. Okay, just imagine both are traveling from A to B. The distance between A to B is say 60 kilometer. 60 kilometer. This KTM bike it covers this 60 kilometer in say 40 minutes. But this City 100 bike it covers say in 1 hour. That is 60 minutes. Okay, if I ask which bike has more power, definitely we'll say that KTM bike. Why? Because see here this bike is doing work. Doing work means what? Covering a distance in less time. But this City 100 bike it is doing work in by taking more time. So that's why we can say that KTM bike has more power. So rate of doing work is known as power. Power means what? In a given time, how much work you will do. Okay, if you do a lot of work, then you have more power. If you do less work, you have less power. Okay, see here. So the SI unit of power, work done we measure in joules and power in time. Sorry, time in second. So joules per second is the SI unit of power. So instead of using this joules per second, we use watt. Okay, so watt is the SI unit of power. So joules per second or watt. Okay, so P is equals to work done divided by time. See here, you know this for example. So then now what is the meaning of 1 watt? For example, we measure power in power equal to 1 watt, 2 watt, 3 watt like that. Then what is the meaning of 1 watt? Okay, if an object, okay, the work done by an object is equal to 1 joule, and it will do that 1 joule of work in 1 second. If an object it will do 1 joule of work in